Hey guys, this is video 2.3.3. Now we're going to go ahead and look at some reaction mechanisms, or how these reactions actually happen. So a chemical reaction depends on particles colliding into one another, so obviously they have to actually run into one another. So if you have something with just two molecules reacting, A2 plus B2 for example goes to 2AB, it's plausible that this happens in one step. So these guys run into each other, stick together in some high energy activated complex, and separate it out into two different molecules, and you have a reaction happening. And that'll happen usually in one step. However, if you have something like this, 4 hydrobromic acids plus an O2, and they go to your products, that's going to be exceedingly slow. So if we waited for all 5 molecules to collide with each other at the same place, at the same time, in exactly the right spot, and with exactly the right amount of energy, it's going to be super slow, just because that's really unlikely to happen. So really, instead of one collision of all 5 molecules all at once, like you're seeing up here, the reaction actually occurs in 3 separate steps, or 3 separate individual collisions. And we call those steps elementary steps. So here we are, all our steps broken down. So 1 hydrobromic acid plus 1 O2, these guys collide, and they form some unstable activated complex here called Huber. I'm just going to abbreviate it Huber, H-O-O-B-R. And that step happens very slowly. Then the next elementary step that has to happen is this Huber has to collide with another one of the HBRs and make Hober, 2 Hobers, so HOBRs, 2 of these molecules. And then those 2 molecules, and that happens really fast. So this collision happens fast. So these 2 molecules need to then collide with 2 more HBRs, and then you get your final products here, and that also happens fast. So the slowest step here is what we call the rate determining step. You can only go as fast overall as your slowest step. So if you kind of think about it as if you're driving in a lane of traffic, you can only drive as fast as the slowest car, right? If there's a single lane and there's one car going really, really slow, you can only go as fast as that slowest car. Same thing is true in molecules. The overall reaction can only go as fast as the slowest step. So step 1, since it's the slowest, would be what we call the rate determining step. Okay, show that these 3 elementary steps combine to give the overall reaction. So just like we've been doing before, we're going to cancel out compounds here that appear on both sides. Cancel compounds that appear on both sides. So I'd like you to go ahead and pause the video now, and I want you to actually go through and cancel anything that appears on both sides and write the overall reaction to prove to yourself that this reaction comes from these overall, or these individual steps. Okay, hopefully you saw that this cancels here. Huber cancels there. You have 2 Hobers there and 2 Hobers there. Anything else we need to cancel? I don't see anything else that we need to cancel. So we have HBRs. We have hydrobromic acid, 1, 2, 3, 4 of them. So 4 HBr plus 1O2 yields 2 water and 2 bromine. And that's the exact same reaction. So that's just the proof that these steps all add up to this overall reaction. Okay, identify any catalysts and intermediates. First we need to define those. So what's a catalyst? So a catalyst is something that you add to a reaction, and it doesn't actually get used up in the reaction. When you're looking at the individual steps, though, you might see it used up, or you will see it used up, but then it'll be regenerated. So in the end, you're going to end up with your catalyst. So say HBr was a catalyst, for example. It's not here, but let's just say it was. So if you had HBr, it might get used up here, but then in the end, you would see an HBr also as a product. And that makes sense because catalysts don't get used up overall in the reaction. So you'd have HBr, maybe it gets used, but then it gets regenerated. So catalysts are present as a reaction, as a reactant, sorry. In the initial step, so in the very first step, you're going to start with it. And then they're regenerated, so then they come out as a product in some following step, and they're not used up again. So here there are none. None here. Intermediates, on the other hand, intermediates are formed in one step and then they're used up in another step. And they don't have to be regenerated at the end. So these are formed and they're not present initially in one step and then used up. So go ahead and pause it and see if you can find the intermediates here. Hopefully you saw that we have two intermediates. So HOOBr was formed here, and then it was used up, never to be seen again. And then HOBr, we had two of those formed, and two of them used up, and then again, never to be seen again. So those are both intermediates. So HOOBr and HOBr are both intermediates here. Okay, so write the rate law, while the rate law for the overall reaction can only be determined experimentally, the rate law for each individual elementary step can be expressed by its molecularity. So molecularity. This is an example. This is molecularity. So basically, however many molecules there are in the reactants. That's what molecularity means. And you'll see what that means in just a second as we do some examples. The rate law then for the overall reaction is simply the rate law for the rate determining step, or the slowest step. So the rate law for the overall reaction is simply the rate law for the rate determining, or whatever the slowest step is. So let's do these examples over here before we move on to these bullet points. So the molecularity here for this elementary step is 1. That's because we only have one reactant. So the rate law would equal rate equals K A to the first power. So that's our rate law, because our molecularity is 1, because we only have one thing there. Okay, let's do the next one. Rate equals, and what's our molecularity here? Well, our molecularity here is 2. We have two things. So they're both A, but there's two of them. So the rate equals K times the concentration of A squared, because our molecularity was 2. There's two things. Okay, let's look here. Our molecularity here, again, is 2. So A and B. So rate, now they're not both A in this case. So K times A to the 1, because there's one A, and B to the 1, because there's one B. Overall, we have 1, 2, molecularity 2. So I'd like you to please pause the video and do the next 3. Okay, the next one, molecularity is 3, so right here, and they're all A, equals K, A to the third power. Here the molecularity is 3, because you have two B's and an A, so rate equals K times A to the 1, B squared. Molecularity here is 3, 1, 2, 3, so our exponents need to all add up to 3, so rate equals K A to the first, B to the first, and C to the first. So now that you know how to do that, I want you to go back up here and do the same thing with our reaction, with our elementary steps. So go ahead and pause the video and see if you can write the rate law for all 3 steps here. Okay, so step 1, the molecularity here is 2, because we have two things, two species. So rate equals K times HBr to the first, O2 to the first. So adds up to 2. The molecularity is 2. Okay, next one, molecularity is 2 again. We have two separate things, so K times HOOBr to the first, HBr to the first. Finally, the last one, our molecularity is 1, 2, 3, 4. So these need to add up to 4. So rate equals K, HOBr, and there's 2 of them, so squared, times HBr, and there's 2 of them, so squared. So 2 plus 2 is 4, 2 plus 2 is 4, molecularity here is 4. Okay, so which step is the rate determining step? Well, it's the slowest one. Oh, slow, step 1. And what's the rate law for the overall reaction? Well, it's the rate law for the slowest step. So we find the slowest one. I wrote my rate law. That's the rate law for the overall reaction. So rate equals K, HBr to the first, O2 to the first. And that's our rate law for our overall reaction. Looking at our next reaction, for example 2, we're just given 2 steps. We don't know if they're slow or they're fast yet, and this graph that goes with it. Okay, so consider the potential energy diagram on the right. Which step is the slow step and how can you tell? So here's step 1 right here, NO2 plus F2 is going to NO2F plus F. So here to here, that's our activation energy 1. This is our activation energy 2 right here. So activation energy 1 is much higher than activation energy 2. So activation energy 1 is going to be the slow step, and that's because it has a larger EA. So if it requires more energy to do, it's going to be slower. So step 1 has the larger activation energy. Okay, so I'm going to just go ahead and label them up here. So this one's going to be slow, that one's going to be fast. We can tell that from our graph. Write the equation for the overall reaction. Okay, to do that, I just need to go up here, cancel out anything that's the same on both sides. So let's see, the only thing I have that's the same on both sides is just fluorine. Everything else is not repeated. So, okay, I have 2 NO2s. Nitrogen dioxide, I have 2 of those, plus a fluorine, F2, is going to yield NO2F. That's our overall reaction. Identify any catalysts or intermediates. Well, there's nothing that was present initially that's also present at the end, nothing that was used and then regenerated, so no catalysts. Intermediates, anything that was formed and then used up. Well, we can see here that fluorine was formed and then it was used up, so intermediates, definitely fluorine. Just fluorine. And then write the rate law for the overall reaction. Well, the rate law for the overall reaction is just the rate law for the slowest step. So that would be our first step here. So our molecularity is 2. So my rate equals K times the concentration of here, NO2, there's just one of them, times F2, there's just one of them. That's it. These add up to 2. Molecularity is 2. That's the slowest step. That's our rate law for our overall reaction. So that's it for that example. So it's not uncommon to see a reaction mechanism in which there's a fast equilibrium that happens before the slow step in a reaction. So, and then the rate law here is a little bit more complicated because the rate law is going to be a combination of both the fast equilibrium and the slow step. So it's going to be both. So here's the steps that you take to solve that. So write the equilibrium expression for the fast equilibrium. So that's that K expression. If you'll remember from your first chemistry class, equilibrium is products over reactants. We haven't gone over that yet in this class, but products over reactants. Solve the fast equilibrium for the chemical that's in the slow step. Write the rate law for the slow step. We've done that before. And then substitute and then combine the constants. I'm going to go through this as an example so it'll make more sense. So consider the following reaction. So here's our overall reaction. And this is the rate law that has been found through experiments. So these are 3 proposed mechanisms. And the question is asking you which one is consistent with the reaction data. So which one would make sense for the data here. So let's go ahead and solve that. So write the equilibrium expression for the fast equilibrium. Okay, so here, actually we don't even need to do that one yet. Let's do this one first. So this is the same as before. So the slowest step is just going to be our overall rate law. So here, our rate would be equal to K times NO to the first, O2 to the first. Okay, does this match this? No, it doesn't. So not consistent. Okay, so it's not mechanism 1. Let's check mechanism 2. So this is where our fast equilibrium is going to come into play. This is where we need to use those new steps. Okay, so mechanism 2, our fast equilibrium. Write the equilibrium expression for the fast equilibrium. I'm going to do this in a different color just so we can keep these separate. So we're going to do our KEQ equals, and then our products over our reactants. So our product is NO3 over our reactants, so concentration of NO times O2. And then if you had a coefficient there, those would go up in the exponents, just like we do with our rate law, but we don't. And then our next bullet point says, solve the fast equilibrium expression for the chemical in the slow step. So whatever is going to be produced in your fast equilibrium here and gets used up in the next step, we're going to solve for this. So basically, we just want to set everything equal to NO3. So we're going to multiply both sides by the denominator here. So doing that, we get concentration of NO3 equals KEQ times NO times O2. Alright, so that's solving for our NO3. Okay, write the rate law then for the slow step. That's our next step. Our next bullet point says write the rate law for the slow step. So just like we've been doing before, nothing changes here. So rate equals K times NO3, concentration of NO. And those are both to the first power. And then substitute the equilibrium expression into the rate law. So wherever I see NO3 here, instead of NO3, I'm going to write KEQ NOO2. So all of this is going to get substituted in for NO3. So I'm going to write that, combining the colors so we can see where they came from. So rate equals K times all of this. KEQ times NO, concentration of O2, and parentheses. Okay, and then our NO. So all I did was substitute that in there. Nothing else changed. Then we're going to combine the two constants, K and capital K, into a new constant K prime. So we have this K and this K. We're going to combine these into a brand new constant, and we're just going to call it K prime. So equals K, so these guys are combined, K prime, and then I have two NOs here, so I have two of them, so my new exponent is going to be 2, so times NO, and I have 1, 2, okay, and then my O2, and we'll have rate equals. So this would be our overall rate law then for this mechanism. So is this the same as this? Is this consistent? All that work, and nope, that one is not consistent with the rate law. So sadly, it's not mechanism 2. Okay, so that's how you deal with a fast equilibrium. Mechanism 3, now we're just going to compare it the same way we have been. Here's our slow step. I'm going to write my rate for the slow step. So rate equals NO and then squared. Is that the same as this? Yes. So the answer then would be mechanism 3. So this mechanism would make sense for this experimentally determined rate law. So your answer then would be mechanism 3 for this problem. But the real takeaway here is how to deal with a fast equilibrium. Okay, so that is the end of this video, but I do want to talk very quickly about the next video before we get there. Video 2.3.4 actually is not me talking, and there's nothing you need to fill in here, but you do need to take some notes. So video 2.3.4 is actually this video here, and you just need to watch that and take notes as they demonstrate each one. It's a really neat video and pretty entertaining. So that'll be your next video.